Hi, my name is Josh Gerganis, and this is Lab 2. So, to introduce Lab 2, it's pretty similar to Lab 1. We're going to be talking about how household objects, which typically are neutral charged, will be able to pick up extra charges depending on what other objects they come into contact with. Also, we'll be observing the different effects that these kind of objects have on each other, whether it be repulsion or attraction, and how to use these effects to determine the excess charge which an object contains. In this lab, we'll use clear tape like we did in Lab 1 to observe the effects of excess charge. However, to differ from Lab 1, in this lab we'll be modeling the charges of the tape as line charges instead of point charges, which will be multiple point charges coming together to form a line. So the basic concepts that I'll be going over in this lab will be Newton's second law of motion, which can be seen in the gravity function as gravity times mass times the gravitational force gives you the force. And then in Newton's third law of motion, we'll be able to see that the electrical force has an equal and opposite reaction, which is seen in the gravitational force. So my measurements were 0.18 meters of the tape. Then I was able to use that to calculate the mass. And from the mass, I was able to calculate or measure the distance between the two tapes that were floating from each other. And then from that, I was able to use the gravitational equation to find the gravity that's pushing down on it. And since Newton's third law, that electrical force is the same as gravitational force, calculating the electrical force with this equation, I was able to plug in gravity and find the charge, rearranging the equation as 1.107 times 10 to the negative 8th coulombs. And then to calculate the number of excess electrons, I just divided the charge of the tape by the charge of electrons. And to find the ratio which the tape gave up of electrons, I just had to do the number of excess electrons and the number of atoms on one side of the tape, and then I was able to use that to find the ratio of extra electrons to the total atoms. To go into the glow script, this is how I created the visual effect of the line charges of the tapes acting on each other, as well as the vectors of gravity and electrical force acting on the tape. So this first slide shows all of the constants that I used in the code, including the Coulomb's constant, the gravity constant, and then also the mass of the tape that I measured earlier. And then for the charge, originally I calculated it to be from my experiment when I read the two tapes and then measured the distance that they were repulsed from each other. However, during when I was going through the glow script, I ended up finding that my model was not in line with what the rest of the function was giving. And so when I changed the charge, the vectors started becoming more line and more in scale with the rest of it. So I found this charge to be more appropriate for my glow script file. And then the bottom, I just put in the E field from the last labs. It's the same, and then I just rearranged it with the information from the line charges here. It is just the function that creates the line charge. And then this is the top and the bottom tapes, and I put in the Y position of the vectors, the distance that I measured between the top and the bottom tape, which floated above each other. Here I was able to find the scale that the vectors needed to be in order to show up on the model. And then the rest of it from the for loop down just shows the electrical force acting on each individual point charge within the line charge that the bottom acts on to the top line charge. And so instead of having just one big force of gravity and force electrical force vectors, I also have individual forces here from the bottom paragraph of code. And then the last part is just to print out the magnitude of the electrical forces, as well as to show the electrical force and gravitational force as vectors. And when all said and done, it came out like this, which is, you can see the white arrow shows the electrical force that the bottom acts on the top tape, and then the yellow is the gravity that is being forced onto the top tape. And then the green vectors are the electrical forces which the bottom tape acts upon the top tape. And then, as you can see, the reactions are shown from their magnitude in the bottom box. And so the magnitude of the charge on one piece of tape was calculated there, although it's slightly different from what I found earlier. However, this is what ClosScript ended up showing me that was the actual more appropriate answer. And so the what if question is, what's the difference between using the point charge versus the line charge? Well, my numbers showed the charge to be slightly more increased when using the line charge, which ended up being more appropriate to real life, because when you use the line charge, it takes into consideration the x values of the electrical force, as opposed to lab 1 when you use the force charge. When you use the point charge, it only took into consideration the y value that the electrical force acted upon each other. So when taking into consideration an extra dimension, it makes it more realistic. So lab 2 and the line charge was more realistic. And in conclusion, the attractive and repulsive effects of charged objects were seen in this lab. The neutral or non-charged object's tendency to pick up and give away electrons was seen in the clear tape. Gravity force and electrical force are equal and opposite to keep tape A, the top tape, afloat. The distance of the tape that I measured was able to show eventually through the calculations the number of excess electrons, as well as the charge on the tape. And then the charge of the tape was able to find the amount of excess electrons that the tape possessed after the experiment, and then comparing the computational difference between the tape as a point charge and a line charge. The line charge is more accurate because it takes into consideration more dimensions.